じゃあ、そろそろライブ配信開始します。Okay, shall we start? Aloha! Welcome to Galaxy Cruise. My name is Kumiko Sato, a public outreach specialist at Subaru Telescope and helmsman of the Galaxy Cruise project. Galaxy Cruise is a citizen science project of the National Astronomical Observatory of Japan, NAOJ. Citizen astronomers classify galaxies captured by the Subaru Telescope on Mauna Kea, Hawaii. The first scientific paper from Galaxy Cruise was published. Today, Captain Masayuki Tanaka will share scientific results reported in the paper. Captain Tanaka, please introduce yourself and start your presentation.
Thank you. Aloha. This is Masayuki Tanaka, Captain speaking. As Kumiko-san said, I'm going to describe the first scientific paper from Galaxy Cruise. I'll try to do that in the easy language. I'm not going to use any technical terms. I hope you will enjoy this live streaming or recording if you look at this later. And also, I will also hope you're also enjoying the ongoing Galaxy Cruise special campaign, which is to classify simulated galaxies. I'll briefly touch on that in my talk later. All right, so can I start?
Yes, please.
Let's see. Hold on a second. No, that's the wrong screen, is it? This one? Can you see my screen?
Yes.
Okay, good. Very good. Then let me start. So, like I just said, I'm going to describe the first scientific paper from Galaxy Cruise entitled Galaxy Cruise, Deep Insights into Interacting Galaxies in the Local Universe. The paper was published in October 2023, last month. So this is really a new paper. It was published in Publications of Astronomical Society of Japan. This is a Japanese astronomical journal. I chose this journal because the Galaxy Cruise is a Japan-led project. This paper is based on your classification results in season 1. And the paper would not have been possible without your contributions. So thank you very much. I appreciate your support and help here. And I'm going to describe this paper in easy language. So here's the first page of the paper. The exact page format is different from journal to journal, but in most journal, you have the paper title at the top of the page, followed by a list of authors, list of affiliations of the authors, abstract, and then the paper body starts. If you're interested in the full paper, you can go to this page so that you can grab the PDF file of the paper. Anyone can look at this paper, but the paper is going to be difficult for you to fully understand because the scientific paper includes a lot of technical terms. But don't worry, I'm going to describe the paper in an easy language today. Good. So I'll start with the motivation of this work. Actually, before I get to that, the structure of this talk is identical to the structure of the paper. So I hope you will feel that you're reading through the paper. So let's start with the motivation. As you know, there are so many galaxies in the universe. The universe is filled with galaxies. And when there are galaxies relatively close to each other, the galaxies will pull each other through gravitational forces. So they could get closer and closer with time, and finally merge to form a single galaxy. And astronomers believe the mergers, galaxy mergers, are very important for galaxies to grow. In other words, the galaxies grow by merging with other galaxies and become more massive and become larger. But unfortunately, astronomers' understanding of galaxy mergers is still somewhat limited, I should say. The reason for that is because I think there are multiple reasons, but at least one of the reasons is that mergers are difficult to find. They are relatively rare objects. And also, when galaxies merge, they sort of characteristic features around the galaxies. Just like the one you see here, this kind of tidal tails. These features are typically very faint. So if you observe these galaxies with a small telescope, you don't see such a feature. But there's a Subaru telescope. It's a big mirror telescope, and the Subaru telescope has conducted a big observing project to take pictures of a large area of the sky with an excellent image quality. And because the Subaru is a big telescope, we can relatively easily find diffuse, faint features of galaxies in the Subaru images. So this is an ideal data set to look for merging or interacting galaxies. But there's another problem, which is merging galaxies are relatively rare. But there are so many galaxies in the images that Subaru took. So how can astronomers find these rare objects among countless normal galaxies? Maybe I should look at the galaxies by one, but I'm sure that's going to take ages. So my solution to this problem was to ask you to help me. And now you see why I'm running a galaxy cruise. And again, the results I'm going to show you today are based on your classifications and season 1. Good. Section 2, galaxy classifications. Let's first of all refresh our memory on the galaxy cruise classification scheme. I think the figure is familiar to you. This is a classification scheme. In galaxy cruise, you are asked 2 to 3 questions. The first question is the morphology of the object you're looking at. Is it elliptical galaxy or is it spiral galaxy? The second question is whether the galaxy is interacting or not. If you say yes, then you go to the third question and choose which features you see around that galaxy. So this is the classification scheme of galaxy cruise. I have carefully analyzed all of the classifications from season 1. There were more than 2 million classifications from season 1. There was many classifications, and it was quite interesting to analyze your classifications. Now, let's first ask how good the galaxy cruise classifications are, and I'll start with the visual check. The top images here are the galaxies for which the majority of people say, these are spiral galaxies. The bottom panels are the elliptical galaxies. And as you can see, these are clearly spiral galaxies, and the bottom images are clearly elliptical galaxies. So this is very good. This is very good. This clearly shows your classification of spiral elliptical is good, at least for very obvious cases. And I also looked at an intermediate case. There are, of course, galaxies, difficult galaxies for which you answer, 50% of you says, say, this is elliptical galaxy. But the remaining 50% says, this is spiral galaxy. So that's an intermediate type. And here's a picture of these intermediate galaxies. These galaxies look interesting to me because these are indeed intermediate galaxies, type of galaxies between spirals and ellipticals. In Galaxy Cruise, we adopted a relatively very simplified classification scheme. We just asked whether the galaxy is a spiral or elliptical. There are more complicated, more complicated a classification scheme in the literature, and many of them adopt this intermediate type. These intermediate galaxies are called lenticular galaxies or S0 galaxies. They are literally between S0, the elliptical and spiral galaxies. And I was surprised to see that the citizen scientists were able to identify these intermediate galaxies. So this was quite interesting to me. Now, let's be a little bit more quantitative. This is a scientific plot, so I should explain this figure carefully. Let me see. So you see a lot of points here. Each point is a galaxy. And so there are about 20,000 points in this figure. And each point is color-coded. The red color means the galaxy is classified as elliptical galaxy. Blue are classified as spiral galaxies. And green is intermediate. Now, the vertical axis shows the color of galaxies. I'm not going to explain this U minus R, what this U minus R means, but let's just say the larger number means the redder colors. And the smaller numbers mean bluer color. Okay, and then the horizontal axis shows the brightness of galaxies. On the right, you have faint galaxies, and on the left, you have bright galaxies. Now, astronomers know that there's a very strong correlation between the color of galaxies and the shape or morphology of galaxies. So I used color as a proxy for morphology to characterize quantitatively how good your classifications are. And I can say that the classifications are actually very good. Let's see. So on the top half of this figure, the points, these are red galaxies. And astronomers expect these red galaxies are elliptical galaxies. And indeed, most of the points here are red points, meaning they are elliptical galaxies. On the other hand, the blue galaxies down here are likely spiral galaxies. And indeed, the points here are blue points, and they are spiral galaxies. So there's an excellent correspondence between your classification and the color of galaxies, meaning that your classifications are very good. I was very glad to see this figure. Right, so this is good. Let's ask how good your interaction classifications are. And here's a gallery of interaction features that you identified. Let's see. So this is galaxies with the significant distortion, tail, fan, and ring. As you can see, for instance, ring galaxies here are all beautiful ring galaxies. And the galaxies down here, all of them show clear, shell or fan features. This is very good. This again suggests your classifications are indeed very accurate. Okay. By combining all the questions we asked in Galaxy Cruise, I was also able to find extremely interesting class of objects, which is violent mergers. Some galaxies are undergoing, are currently in the very violent phase of mergers. And as you can see in this figure, these galaxies show extremely complex shapes, suggesting how violent the mergers can be. So this is a very interesting sample of mergers. I will discuss the violent mergers a little bit further later in this talk. Good. Next, I'm going to compare our classifications with earlier studies. So when you do scientific work, it's very important to compare your results with previous results. Good. I'm going to compare with Galaxy Zoo 2. As you might know, Galaxy Zoo is a precursor, probably the biggest citizen science project on galaxy morphology. It was a very successful project. And their latest catalog is can be obtained from their from Galaxy Zoo 2 project. And I took their catalog. And the left figure compares the spiral probability between the Galaxy Zoo 2 and Galaxy Cruise. And again, each point is a galaxy. So we are comparing a classification, elliptical spiral classification on a galaxy by galaxy basis. If our classifications are fully consistent with the Galaxy Zoo 2, then we can expect all the points should line up here. There are a bunch of points here. That's good. Bunch of points here. Good. But you also see a bunch of points down here. Galaxy Cruise says these are spiral galaxies. But Galaxy Zoo 2 says, no, these are elliptical galaxies. So we are sort of inconsistent. Now let's look at the images of these galaxies. The top panel shows the images used in Galaxy Zoo 2. The bottom panels are the images of the same galaxies, but they used in Galaxy Cruise. So the bottom figures images are taken with Subaru. As you can see, so these are the same galaxies. The top and the bottom panels show the same galaxies, but taken with different telescopes. As you can see, all these galaxies show beautiful spiral arms in our images, while it's not very clear in the previous images. So I think this suggests that our classifications are likely more accurate than the Galaxy Zoo 2 classification. Now, what about interacting galaxies? This is basically the same figure, but for interaction probabilities. And again, if we are completely consistent with the Galaxy Zoo 2, we expect all the points along this line. Again, we observe lots of data points and galaxies down here. If we look at the images, we can clearly identify beautiful interaction features in our images. This is the power of the Subaru Telescope. Like I said earlier, you don't see interaction features if you observe with the small telescope. The GZ2 images is based on the images taken with the small telescope. But we are using an 8-meter telescope, so it's much bigger. And if you use the big telescope, then you can easily see faint features, interaction features around the galaxies. So overall, I think it's fair to say that our classifications are better than the Galaxy Zoo 2. And that makes our work very unique. Okay, now let me move on to discuss the properties of interacting galaxies. This is a kind of difficult part, but I try to use a easy language. First, I will focus on star formation activity of galaxies. As you might know, galaxies form stars. There's a lot of gas and dust inside the galaxies. Sorry, and these the stars form out of these condensed gas and dust. The rate at which new stars forms is different from galaxy to galaxy. And in this figure, I'm looking at how actively or how frequently new stars form in galaxies. The horizontal axis shows the activity of star formation. Let's not look at the numbers here. Let's not even look at the complicated technical terms here. Let's just say if you go to the right, then it means the galaxies are more actively forming stars. If you go to the left, then galaxies are less actively forming stars. And the curves here show the distribution of galaxies. Now, the black curve here is for normal galaxies. And on average, these galaxies are forming stars around this rate. Yeah. But if you look at interacting galaxies, then which is shown by this red curve, as you can see, this red curve is shifted systematically to the right, meaning that interacting galaxies are more actively forming stars than normal galaxies. This is particularly the case for violent mergers. It's a little hard to see this pink line, but the violent mergers are this pink line. So the violent mergers is shifted even to the left, to the right, from the typical interacting galaxies. So the violent mergers are really sort of starbursting galaxies. This is a very interesting result. Next, black hole activities. There are supermassive black holes at the centers of massive galaxies, and these black holes can be active when some material falls onto the black hole. And then this figure shows what fraction of galaxies host active black holes. If you look at the normal galaxies that are not interacting, they host, about 28% of them host active black holes. Let's not look at the number in the brackets. Let's just look at this, the top number, 0.282. This means 28% of the normal galaxies host active black holes. If you look at interacting galaxies, then the fraction increases to 35%. This is a statistically significant increase. So this means that when galaxies merge and collide, the central supermassive black hole can be activated. And this is particularly the case for violent mergers. About 42% of violent mergers host active black holes. So this is another interesting result. Why interesting? Because previous studies on these merging galaxies have reported contradicting results. Some researchers say, the star formation activity is enhanced during the mergers, while other researchers say, no, it's not enhanced. Some people say, the black hole becomes active when galaxies merge, but others say, no, they don't get activated. But our results clearly show that both star formation and black hole activities are enhanced when galaxies merge and collide. This is a very good, clear result. And I think, our result here is a very big, very significant contribution to the long-standing issue of, whether, the internal activities of galaxies are enhanced or not during the merger. So that was the main scientific result. Let me conclude with the future prospects. As you know, we are currently running a special campaign to classify simulated galaxies. This is very important for us. I, quantitatively characterized your elliptical versus spiral classification using color as a proxy. That was very important, but I couldn't do this kind of analysis for your interaction classifications because there's no such a proxy to replace interactions. So at this point, we don't have a truth table of which galaxies are actually interacting. In other words, we don't know how accurately you could classify interacting galaxies. And that's the reason why we are running this simulation campaign. In a computer simulation, we know which galaxy merged when. So we sort of, in a sense, we have a truth table. So by comparing with your classification with the truth table, then we can say, what fraction of galaxies are indeed interacting. And this understanding is a very important step forward. And of course, season 2 is still ongoing, as in good progress. In season 2, we ask you to classify relatively faint galaxies. That's because I wanted to look at the properties of faint galaxies carefully. Galaxy properties are strongly dependent on the brightness of galaxies. Bright galaxies are different typically from faint galaxies. So it's important to extend the brightness range to better understand better understand the galaxy mergers. Of course, it's hard. It's hard to classify this kind of faint galaxies, but your help, your classification will be very much appreciated. Okay, that's basically all I wanted to say. But let me, as a summary, let me say again that we published the first scientific paper in Galaxy Cruise, and that paper would not have been possible without your contributions. So thank you very much. I appreciate it, and I hope you continue to enjoy Galaxy Cruise. And I'll stop there. Thank you very much.
Thank you so much, Tanaka-san. Thank you so much, Captain. Yeah. So as a Captain repeated again and again, your classification results was awesome. And thanks to the high quality data of Subaru Telescope and your excellent classification enable the captain to analyze. And we could make big discovery like the previous classification. They believe it was elliptical, but now we know it is spiral or something. Okay, so we don't have any question on the chat screen, but so maybe I hope you enjoy the many discoveries. And your classification changed the picture of morphology of galaxy and galaxy interaction and activity of galaxy. Thank you so much. And now, as Captain said, now we are conducting special campaign. Oh, before talking about the special campaign, now, Captain, so our paper result, the Galaxy catalog is now available, right? Would you like to add something?
Yes, the classification catalog is now publicly available. I used that catalog to obtain the results I presented today, but it's such a useful catalog. The scientific value of the catalog is very high, so it's probably not very good if I just keep the catalog myself. So I decided to make that catalog publicly available to the researchers from all over the world, and I'm hoping that they can explore the catalog further and make new discoveries. In particular, the catalog is going to be quite interesting for machine learning applications. This is the highest quality morphology catalog statistically for a statistically large sample of galaxies. And again, so this is an ideal sample to train a machine to automatically classify galaxies. And I published the paper about a month ago, and also the catalog. I already started to get emails and inquiries from researchers from the world. So I hope researchers, everybody, will enjoy the catalog.
Great, thank you so much, Captain. So we released the Galaxy catalog on the Galaxy Cruise public official website. So if you are interested in catalog, please go to our website and click for researchers and get a catalog. So there are more than
20,000 objects.
Yeah, right. 20,000, 20,000, more than 20,000 galaxies. Yeah. Okay, and also sometimes, some researchers contacted Tanaka-san, some results, and some researchers have a presentation at the ASJ, Astronomical Society of Japan, via meeting. So we hope more researchers use our Galaxy catalog. And then the last announcement is now we are conducting a special campaign classifying simulated galaxies. And so the season 2, thank you so much for classifying many faint small galaxies, but different from season 2, during the special campaign, we hope you enjoy bright galaxies like season 1. So you find many interacting galaxy with clear distortion or long tails. So please keep enjoying classification in the special campaign. And we also now preparing for the year-end New Year campaign. So we are preparing some present to who classify many galaxies, more than 1,000 galaxies. So please stay tuned. Okay, so Tanaka-san, is there anything you want to add something?
No, like I just said, I also hope that you continue to enjoy Galaxy Cruise, and I'm hoping that I can use your season 2 classifications and make new discoveries. So thank you very much.
So much. Thank you so much. So thank you so much for watching our live streaming, and we hope to see you again in winter, maybe end of December. Thank you so much for classifying many, many galaxies. Please keep in touch. Thank you so much. Mahalo nui loa. See you
Bye.
again. Bye.